A self-driving car sees a stop sign. It reads it perfectly. Nightmare. Now someone puts a few tiny stickers on it. Nahrik. The car no longer sees a stop sign. It sees a speed limit sign, and it accelerates. That is not science fiction. That is a published, peer-reviewed adversarial attack from 2017, and the neural network had no idea it was fooled. So here is the terrifying question. If AI systems can be tricked this easily, how do we trust them with anything critical? Here is the core idea. Neural networks classify inputs by finding patterns. Adversarial attacks exploit the geometry of that learned decision boundary. An adversary adds a tiny, carefully crafted perturbation. Humans cannot see it. But mathematically, it pushes the input across the boundary into the wrong class. The most famous method is FGSM, the fast gradient sign method, proposed by Goodfellow and colleagues in 2014. It computes the gradient of the loss function with respect to the input, then nudges each pixel in the direction that maximizes the model's error. One step. That is all it takes. The result, an image of a panda that a human sees as a panda, but the model classifies as a gibbon with 99.3% confidence. The pixel change is less than 1% of the image's dynamic range. The model is completely wrong and completely certain. FGSM is just the beginning. Now here is the part nobody talks about. Attacks have evolved into iterative methods like PGD, projected gradient descent, which takes many small steps and is far more powerful. Then there are patch attacks, physical stickers printed in the real world, no access to model internals needed. And then there are black box attacks. The adversary has no access to the model weights at all. They query the model repeatedly and use the responses to estimate gradients. Real API attacks against real production systems. In 2019, researchers demonstrated a black box attack against the Google Cloud Vision API using fewer than 1,000 queries. The model was fooled on 35% of test images, with no access to weights, no source code, just an API. That is the threat model security engineers need to think about right now. This is not just an academic problem. Wait, it gets worse. Adversarial attacks have been demonstrated against facial recognition at border control, against malware classifiers inside commercial antivirus engines, against NLP models used for content moderation. The attack surface is everywhere AI makes a decision. In 2020, researchers at McAfee showed they could trick a Tesla Model S into accelerating to 85 miles per hour by placing a 2-inch piece of black tape on a 35 mph speed sign. The Mobileye camera system misread the sign. Adaptive cruise engaged. No software exploit. No network breach. Just carefully placed tape. And in 2023, researchers at Carnegie Mellon published universal adversarial suffixes that bypass safety alignment in large language models, including GPT-4. The attack transfers across models. One suffix, many victims. The threat is not theoretical. It is shipping in production systems today. So, how do you defend against this? The honest answer? It is hard. There is no silver bullet. But adversarial training is the most battle-tested defense. You augment your training data with adversarial examples and retrain. Models trained with PGD adversarial training show real robustness improvements. The trade-off, a 2 to 5% drop in clean accuracy. Input preprocessing adds another layer. JPEG compression, feature squeezing, and randomized smoothing can reduce gradient-based attack effectiveness. For production APIs, certified defenses using randomized smoothing provide provable robustness guarantees. And ensemble diversity helps. If your classifiers do not share the same decision boundaries, a single adversarial example is unlikely to fool all of them simultaneously. No single defense is unbreakable. The field is a constant arms race. But layering these defenses raises the cost of attack significantly. For security engineers deploying ML systems, treat adversarial robustness like you treat patch management. It is not optional. It is part of your threat model. Case 1. McAfee Tesla Attack 2020. Researchers placed a 2-inch strip of black electrical tape on a 35 FGSM sign. The Mobileye IQ3 camera misread it as 85 FGSM. The car's speed assist engaged. This was a physical adversarial patch. No code injection, no network access. Just an understanding of how convolutional filters respond to edge patterns. Case 2. The GCG LLM attack from Carnegie Mellon 2023. Zhu and colleagues found a universal adversarial suffix using gradient-based optimization over token embeddings. The suffix looks like gibberish, but appended to any harmful request, it causes GPT-4, Claude, and other aligned models to comply. One suffix, many models. Full safety bypass. Both attacks share the same root cause. Models are optimized for accuracy on clean data. They have no explicit incentive to build robust, human-aligned decision boundaries. Until adversarial robustness is a first-class training objective, every deployed model carries this risk. Every single one. Here is what you need to take away. Adversarial attacks are a fundamental property of how neural networks learn. If you are deploying ML in a security-critical system, adversarial robustness is not a feature. It is a requirement. Apply adversarial training. Layer your defenses. Monitor your API for black box probing. The arms race between adversarial attacks and defenses is real.